In the simple I/O operations we've seen so far, laziness plays a key role. And this can be illustrated in the following examples. So I have a reference here to a dictionary, and it's a very large dictionary. And this function here will compute the first word of a given file. So it will read the file. It will take the contents of the file C and apply lines and then the head. So it'll break it into lines and take the first line. And then we'll print that first line on the screen. So this is an I/O operation. So we can try this one out. We can take the first word of the dict. Now this is a big dictionary, but the first word is very quick to compute. If we compare instead with the last word, the corresponding computation here, where we've replaced head by last. Okay, it was also pretty quick. I was hoping that there would be a visible difference in speed, but there doesn't seem to be. Okay, I had to pause there to think for a second how to best show the difference in speed. So I've written a little bit of code to actually do that, and it's a speed test. So it basically takes two I/O computations and performs the first one and then the second one and compares the speed. So this might not be a completely fair test, but the point here is that it's still a bit too fast to actually see the difference between the two. So let's do a speed test. I've restarted the interpreter down here. So let's do a speed test with first word of the dictionary compared to last word of the dict. Okay, so you can see there's a, I mean, they're both pretty quick. The slower one is 0.1 of a second. So the first word is A and the last word is Zogeton. And the first one is about 100th of the speed of the second one. Okay, so what's the reason behind that speed difference, even though it's hard to see with the naked eye? The reason is that file I/O is lazy. So when we perform a read file, we're actually lazily reading the file, which means we don't actually read in the whole file. In fact, we don't read all of it at all unless we need to read it all. And so first word will not read the whole file, but actually just read the first line of the file. And why is that? Well, because that's the only part of the file that we actually need to compute the result. And so this computation is not triggered until we actually require to actually print it on the screen. And in order to compute this, we only need to actually read the first line of the file. But because of the way streams and lists work, when we want to compute the last thing, well, we have no choice but to read the whole file because we have serial access when we're using read file. So we're reading from start to finish. So another common pattern of I/O is to use a function as a kind of pipeline processor between the standard input and the standard output. And so visually, we have the standard input stream. That's the stuff we're typing at the terminal, for example, or if we have a standalone program, the stuff that we send to that program. And this is the output. That's the stuff typically in our interpreter that's printed on the screen. And what we want to do is take the stream of data that comes in and process it using a string transformer function, a function from strings to strings, to produce some output. And so this computation pattern has the name interact. It's one of the standard functions. You simply take a string processing function and it turns it into an I/O action, which reads from the input, passes the data through the function to the output. Now, because the function can use lazy evaluation, it means that we can see output before we've seen all of the input. In fact, we don't know what all of the input is. So it's important that this is a lazy function, a function that can compute lazily. That means it can compute using parts of its input in order to produce parts of its output. Let's take an example of this. Let's suppose we want to, line by line, do a URL encoding. So URL encoding is the encoding you would typically use to encode various characters in a way that can be easily transmitted, or for example represented in a web URL. For example, the space character is not permitted there, so you have to encode that with something like %20 or something like that. Okay, so I've imported from some library a URL encode function. What is the URL encode? What's the type of that? Oops, in the wrong window. The type of URL encode is just a string processing function. So, for example, URL encode, I said something like the string with a space in it. So what does that encode to? Yeah, %20 is the URL encoding of a space character. Okay, so this is not terribly important. But the example I want to use is this function here. This is also a string transformer function. It line by line, takes a line, applies the URL encode function, and joins the lines back together again. So this is a line by line URL encoding function. Because URL encode doesn't work by character, so we have a big string coming in. We need some way of breaking that down, and I've chosen in this example to break it into lines. So given this string transforming function, we can turn that into an interactive function using the interact combinator, thanks to the fact that we have lazy evaluation. So let's try this out. Encode lines. Okay, now it's waiting for me to type a line of text, and then it transforms that line of text using URL encode, and then we can have the next line, a bunch of other characters which also get their corresponding encodings. And I'll just terminate that screen. Oh, I killed my whole Haskell. Okay, you get the point. Lazy evaluation plays nicely in these examples with I/O, because I/O processing on streams is a natural fit for lazy evaluation.